Yaskawa America's Technical Training Services would like to welcome you to the Braking Methods Part B e-learning module. My name is Paul Anderson and I am a Drives Product Training Engineer with Yaskawa America. I will be your instructor today as we go through this e-learning module. The purpose of this e-learning module is to provide a basic overview of how to configure the available braking methods in a Yaskawa AC drive. For a review of the available braking methods, please take the e-learning module entitled Braking Methods Overview. During this course, we will cover the four main types of braking: DC injection, high slip braking, dynamic braking, and line regeneration. DC injection can be used at times other than just deceleration to a stop. The first step in setting up DC injection braking is to determine when you would like the DC braking to occur. The first condition is while the motor is decelerating to a stop. While the motor is stopping, DC injection can either occur throughout the full range of deceleration or only after the motor has ramped down to a certain frequency. This will aid in providing additional holding torque at low speeds. The second condition is to provide braking to stop motor rotation prior to a run command being issued. This can occur either through a digital input commanding the drive to DC inject, or it can occur for a predetermined amount of time once a run command has been issued. Let's first look at full range DC injection. The diagram on the left shows the output frequency of the drive over time. When the run command is removed, the drive is running at some output frequency. The drive base blocks for the time programmed into L203. Base blocking is used to allow any residual magnetic fields to decay in the motor so that overcurrents don't occur when sending the motor new voltage. After the base block time is finished, the drive begins sending DC injection to the motor for a certain amount of time. The time is dependent upon the output frequency and parameter B204, which is the DC injection time at stop parameter. The graph on the right shows how this time is determined. If the drive is running at 10% output frequency, say 6 Hz on a 60 Hz maximum frequency, then the drive will DC inject for the length of time in parameter B204. However, when the drive is running at the maximum output frequency, the drive will DC inject for 10 times the length of the time in parameter B204. The reason for scaling the length of time DC injection occurs is because the faster the motor is rotating, the longer it will take to stop. A motor running at full speed will need the maximum length of time to stop, whereas a motor running at only 10% speed will require a shorter time to stop. To enable full-range DC injection, the stopping method, parameter B103, must be set to DC injection to stop, setting 2. This will cause the drive to DC inject anytime the run command is removed. Note that DC injection is not used in flex vector control. The base block time allows for the residual magnetic motor fields to decay prior to sending new voltage to the motor. Parameter L203 sets the minimum base block time. L203's factory setting is size dependent because larger motors have longer time constants that require additional time for the residual motor fields to decay. If an OC or OV fault occurs, consider lengthening the base block time. The amount of DC current sent to the motor is dependent upon parameter B202. This parameter is set in terms of the drive's rated current. So on a drive rated at 3.6 amps, setting parameter B202 to 100% will send 3.6 DC amps. As mentioned previously, the length of time used during full-range DC injection is dependent upon the setting of parameter B204. B204 can be set for up to 10 seconds, making the maximum length of time for DC injection 100 seconds. To set this parameter correctly, determine the length of DC injection time required at full speed and divide that number by 10. DC injection can also be programmed to occur for a programmed length of time after the drive has ramped down to a stop. This is known as DC injection at stop. Note that in order for DC injection at stop to work, the stopping method must be set for ramp to stop. DC injection can also occur immediately after a run command has been given to bring a coasting motor to a stop or build up initial excitation in the motor. This is called DC injection at start. This diagram shows both DC injection at start and DC injection at stop. When the run command is given, the drive DC injects for the length of time programmed in parameter B203. Once that time has elapsed, the drive will begin the normal acceleration by starting at the output frequency set in parameter B201. For instance, if B201 is set to 6 Hz, the drive will DC inject and then begin outputting to the motor at 6 Hz. The drive will then run until the run command is removed. Once the run command is removed, the drive will begin ramping to a stop based on the active deceleration time. When the output frequency drops to the level in parameter B201, the drive will begin DC injecting. Again, assuming B201 is still 6 Hz, once the output frequency reaches 6 Hz, the drive will stop outputting frequency and immediately send DC to the motor. The DC injection time continues for the length of time programmed in parameter B204. Once this time is up, DC is no longer sent to the motor and the motor is no longer under control of the drive. All of the parameters required for DC injection at start and stop are shown here. The DC injection start frequency is the minimum frequency that the drive will output. The DC injection current level must be set for using this type of DC injection as well, and it cannot be controlled in flux vector control mode. Both DC injection time at start and stop have a maximum time of 10 seconds. When using the DC injection at stop function, parameter B204 is not scaled based on the output frequency as it is when using the full range DC injection function. Once the drive reaches the minimum frequency, it will only output for the length of time programmed into parameter B204. If more than 10 seconds of DC injection is required at either start or stop, then using the next type of DC injection braking, a DC injection digital input, will be more effective. DC injection using a digital input can be utilized once a multifunction digital input has its function selection programmed to setting 60. This timing diagram shows both the output frequency of the drive and the status of the digital input set for the DC injection function. Without a run command being given to the drive, the DC injection digital input is closed. Once the input is closed, the drive outputs DC current at the level programmed into parameter B202. The drive continues DC injection until the digital input is opened. The drive then receives a run command, and the drive begins running the motor based on the frequency reference. During the normal run sequence, the DC injection digital input is closed again. However, the run command overrides the DC injection digital input so that even though the digital input is commanding DC injection, the drive will follow the run command and frequency reference instead. With the digital input function left closed, the run command is removed and the drive begins its stopping method. Once the stopping method is completed, the digital input function is obeyed since the run command is no longer present to override the DC injection command. As you can see, DC injection will automatically begin once the stopping method is completed. There is no need to cycle the DC injection command. DC injection continues until finally the digital input is opened and DC injection ceases. The only two requirements for configuring DC injection using a digital input is to set the DC injection current level and to configure a digital input to perform the DC injection braking function. Again, the digital input function for DC injection braking is setting 60. The high slip braking method is only available in the V/F control methods. Set the control method to V/F or V/F with PG if you plan on using the high slip braking function. The drive is commanded to start the high slip braking function by a digital input. An available digital input must have its function selection programmed to setting 68. This timing diagram shows how the high slip braking function works. While the run command is active, the high slip braking digital input is closed, commanding the drive to perform the high slip braking function. Immediately, the drive begins to base block. Base block allows the residual magnetic motor fields to decay so that no overvoltage or overcurrents will occur when the drive begins sending the motor new voltage. Once the base block is finished, the drive begins stepping down the output frequency to force the motor into a large negative slip condition. This makes the motor an inefficient generator so that the regenerated energy is dissipated from the stator and rotor losses. At some point after the high slip braking command is given, the run command is removed. The high slip braking command has priority over the run command. If the run command is not removed, it must be recycled for the drive to run after the high slip braking function has stopped the motor. The current seen by the motor is limited by parameter N302. Faster stops can be accomplished by using more current, but this also creates more heating and reduces the available duty cycle. Although most of the regenerated power is consumed by the motor, some is sent back to the DC bus. The DC bus voltage is regulated so that it will not increase beyond 90% of the overvoltage trip point. While the high slip braking function is active, the high slip braking command is removed. This does not affect the high slip braking function because once the command is given, the drive will bring the motor to a complete stop. As the motor speed drops and begins approaching the output frequency, the current drops as the motor slip decreases. The motor continues slowing down until it reaches the minimum output frequency set in parameter E109. Because the motor is no longer regenerating, the DC bus voltage drops back down to its normal operating level. Once the minimum frequency is reached, the drive holds the motor at the minimum frequency for the time programmed into parameter N303, which is the high slip braking dwell time. This time is used to bring the application to a steady state to prevent continued motor rotation once the high slip braking has completed its function. After the high slip braking dwell time, the drive DC injects for the length of time programmed into parameter B204 and the motor comes to a stop. Once the drive completes the high slip braking function, it will then be able to receive a fresh run command. All of the high slip braking parameters are found in the N3 group. Parameters N301 and N304 are used to set the width of step down in the output frequency and the overload time for the high slip braking function. These parameters are optimized and usually do not need adjustment from the factory. Parameters N302 and N303, however, are adjusted by the user to meet the application requirements. N302 should be increased if the drive does not stop in an amount of time that is short enough for the application. N303 should be increased if the application does not come to a full stop once the high slip braking function has been completed due to load inertia. To adjust the dwell time, simply change N303 as needed. The F7 price book lists part numbers for standard braking resistors and transistors. These packages are rated for a 10% duty cycle and develop between 100 and 150% braking torque as listed in the price book table. Resistor and transistor packages listed in this table are suitable for handling nearly all applications. On applications 5 horsepower and below that require only a 3% duty cycle, a heatsink mounted dynamic braking resistor may be used. However, for applications requiring larger duty cycles, contact a Yaskawa applications engineer about properly sizing the dynamic braking packages. Let's look at an example of selecting the dynamic braking components. An industrial washing machine uses a 30 horsepower drive and is required to stop after spin cycles. Using a standard duty cycle, what dynamic braking components are used on this application? Because the application uses a standard duty cycle, the components listed in the dynamic braking section of the price book are sufficient. This is a portion of the table listed in the price book. First, find the line that matches the size of the drive. Then, look across and see if any transistors are required for dynamic braking. This particular drive does require transistors. Listed in the transistor section are the part number, quantity required, and price of the option. For this application, 2 transistors are required, and the part number is CDBR 2022B. Looking under the resistor columns, we see part numbers, quantity required, list prices for part number, configuration, and lastly, the total price of installing all dynamic braking components on the drive. The part number and the quantities are shown in the first 2 columns of the resistor section. This model requires only one braking resistor module with the part number URS 000135. Once the dynamic braking components have been received, install the dynamic braking resistors and transistors as shown in the user's manual. The user's manual provides installation instructions for all of the available component configurations. The drive comes equipped with a stall prevention that is used to limit deceleration when the DC bus rises too high. This function must be shut off when using dynamic braking, or else the drive will not fully allow dynamic braking to perform its duty. To disable stall prevention during deceleration, set parameter L304 to setting 0 or setting 3. Setting 3, stall prevention with braking transistor, allows the drive's stall prevention to work in conjunction with the dynamic braking function. On the smaller size drives, 5 horsepower and below, It is possible to have a Yaskawa 3% heatsink dynamic braking resistor as an option. If you are using the heatsink resistor, parameter L803 should be enabled by setting L803 to setting 1 for protection provided. This function monitors the resistor usage to indicate when the resistor has been overloaded. Due to the complexity and uniqueness of line regeneration, we will not discuss the specifics of line regeneration in this module. For questions regarding line regeneration, consult the Yaskawa Applications Engineer regarding how to configure your application for this specific braking method. Thank you for attending this Yaskawa America eLearning module. We greatly appreciate you taking the time to learn more about our products. If you would like additional training, please contact us through any of the methods above. Thanks again and have a great day.